Hello all, I am Tarun Kumar from Vellore Institute of Technology, here to present our project on low-cost gesture detector using neural networks. So, what motivated us to do this project? Few months back, our mentor showed us this video on Mayo Talmix Labs, which is nothing but a wearable gesture detector that could be used to detect hand gestures using a technology that is EMG. However, it is much expensive for a common man to buy it and use it. So we wanted to create such a device for a much affordable price. So that is our main objective, and that was our motivation for this project. Looking at the previous work at this field, majorly they classify gesture detection into two types. The first one is to use vision-based systems and use image processing to identify the gesture detection. And the second type is to use accelerometers and gyroscopes for identifying the hand patterns. However, people still use heavy bulky PCs for identifying the patterns since it involves heavy data. So we wanted to create a device that does not require any external PC or as such, and we wanted to identify the pattern by itself without any need of other devices so that it is more compact. So our gesture detector has this kind of an architecture where it has a microcontroller which is Texas Instruments MSP430, which is a very robust and low cost microcontroller. So this is connected to an accelerometer which gives the acceleration with respect to all three axes, that is X, Y, Z, and the microcontroller will detect the correct pattern and it will send the pattern to the other end application through this Bluetooth. Of course, it is powered by a power source which is regulated by LM1086, a Texas Instruments voltage regulated chip. So we have developed two types of applications for our gesture detector product. One is development of an unmanned vehicle where we have developed a car-like structure that could be driven just by hand gestures instead of any remote controllers or devices like that. So it has a microcontroller again, Texas Instruments MSP430, which is connected to a Bluetooth. Here the Bluetooth receives the code from the gesture detector, that is, it receives the correct pattern. So this pattern is then decoded by the microcontroller and accordingly it gives directions to the motor driver. We have used L293D, a quadruple H-bridge motor driver from Texas Instruments, to drive 4 motors so that the structure moves forward or backwards, left or right, and controls like that. It also has a separate power source for the microcontroller and a separate power source for the motor. The next application which we have developed is PC interface. Nowadays, almost all PCs are equipped with the Bluetooth module. So the user doesn't have to buy any separate module as such. He just has to buy this gesture detector and have to connect with the PC using a software which we have created using Visual Basic. So we have created a Windows-based app that could be used to connect our gesture detector to the PC so that we can control almost anything in a PC. Implementation. So in implementation, the main part is learning vector quantization. The learning vector quantization is a type of a neural networks that is very easy to implement and train. The reason why we opted for LBQ is that it doesn't involve complex mathematical operations. It just needs operations like subtraction and multiplication. So in training, what happens is we first acquire known inputs from the user. Say for example, the user gives 10 same patterns and 10 other unique patterns. So we have 20 input samples and we know the exact output for those 20 input patterns. So we load this and then we initialize weight vectors. In this case, there are 2 patterns, so there will be 2 weight vectors. So for each and every training sample, say we take the first training sample and we find the Euclidean distance between this first sample and these 2 weight vectors. So whichever weight vector comes nearer or lies closest to the input vector will be the winning weight vector. Say for example, here the winning weight vector is W1. So the output is pattern 1. If that pattern is actually true, because we know the output for these input samples, so if it is actually true, we push this weight vector towards the input. If it is wrong, we push it away from the input. So like this happens for all the known input samples and goes on. So after many iterations, we will get the updated weight vectors. In this case, we have two weight vectors since we have two patterns. So we then put this weight vectors into Texas Instruments microcontroller so that it acts as a standalone gesture detector, and when an unknown pattern is given to this MSV430, it will correctly identify what pattern it belongs to. It just finds the distance between the unknown pattern and these two weight vectors, that is W1 and W2. So whichever lies closer will be the output. Say if W1 is closer to the unknown input, so the output would be pattern 1. So that's how LVQ works. So when it comes to hardware implementation, this is how our gesture detector looks like. It's a small device, a compact device, which has all the modules inside. So inside, the main module is the Texas Instruments MSV430 chip and the voltage regulator, and this is an accelerometer and a Bluetooth module to send the patterns to the end applications. And this is a battery to powering up the whole source. And this is our unmanned vehicle. It has 4 motors and a Bluetooth device that will receive the correct pattern from the gesture detector and given to the MSV430, that is again connected to the L293D motor drivers, which would move this device forward or backward according to the pattern given by the user. So this is our application for PC. We have developed this Windows-based app for controlling 2 applications. The first one is to control the media player, that is like changing the song or increasing or decreasing the volume, etc. And the second one is controlling a PowerPoint, that is like going to the next slide or going to the backward slide, things like that. So as you can see, these are 2 unique graphs. So this first graph represents an unique pattern given by the user. This one is another unique pattern given by the user. So what these 3 lines are nothing but the acceleration data with respect to X, Y and Z. So this is how the patterns differ. And this tabular column shows an example of the UMV data, that is unmanned vehicle. See, for example, the user gives the action as move forward. So that particular action is identified and then decoded into the pattern 001 by the gesture detector, and it is sent to the UMV, which again has a Bluetooth, which will receive this 001, and accordingly the particular microcontroller will send the action to L293D motors so that the unmanned vehicle will move forward, and so on for the other actions. So we acquired 120 samples and we used 100 samples for training the LVQ network and 20 samples for testing. And for this 20 sample testing, we have acquired results of 99.96 accuracy as classification accuracy. So the main objective of this project is to reduce the cost of this product to as low as possible, and I think we just have achieved that. It costed us about less than 1000 rupees, and when it comes to mass production, it may even go down. So we did create a low-cost gesture detector that could be used for many endless applications. It may not be just for driving an unmanned vehicle, but it could be still applied to maybe driving a wheelchair. You just need hand gestures to make the wheelchair move forward or backward or left or right, and use it for a TV remote control. Use just hand gestures to change the channels or something. And so this would appear as a much cheaper alternative to many other gesture devices that are existing in this era, which are much expensive. When it comes to the future work, we may want to reduce the size of this device still further and include rechargeable power source. And when it comes to limitation, this particular device could not handle very complex patterns at this stage yet. We are still working on that. So these are our references for the project. Thank you.